Alright, so today integration by substitution. Now, as I already mentioned, we've already been doing a little bit of this. Simply, when you let u equal to something and then use that to help you simplify what you're working with. Effectively, it is the chain rule in reverse. Alright, so formally, if I have the integral of fx dx, then what I'm doing is I'm replacing that, changing the function to be not in terms of x but in terms of u, and then where the chain will be du dx is in there. Times by dx, and then effectively the dx's eliminate each other, and so then you have your function integrating your function with respect to u, and so this function here in terms of u is less complicated than one in terms of x. Alright, so let's have a look at a few different types. So first of all, so there's three here. So one of them's circular function. One's a polynomial of sorts. And the other one's a bit of a mix. Okay. So the thing is what we choose to be our u. So let's have a look at the first one. So A, so we want antiderivative of sine x cos squared x dx to get the antiderivative. So we've got two choices here. We've got the sine and we've got the cos, and kind of which one is it that we want to choose to be our u, and the answer to that question, so for this one here, a hint if you like, is you want to choose u from the even power. So when we look at that, we've got sine x and then cos squared. So sine x is sine to the power of 1, cos x is power of 2. So that's the even power. So we want to choose all u to be cos. Alright, so let u equal cos x Because when we differentiate that, differentiate cos, you get negative sign, don't you? Alright, so let's have a look and see what happens then. Okay, so from there, from rearranging from that, you get the dx would be du over negative sign. Alright, so far, so good. So now if I then change my sin x cos squared x dx into things with u in them, the sin x is just there, cos squared, cos was u, so it's u squared, and dx is du over negative sin x. What do you notice? Sign cancels, yep. This negative here, I can put that out the front.
Sorry, why don't you anti-differentiating the sign? Just because it's easier to cancel it?
So we would have to make a choice
Yeah.
for our u, either to be
Yeah,
sine or to be cos.
Yeah.
So the hint when you're choosing it is you look at which one's got the even power,
Yeah.
and you make that
But down the bottom,
down
yeah,
there.
why haven't you differentiated the sign there? Anti-different.
Here,
Yeah.
because they cancel.
So when it's convenient to cancel, just
Cancel
don't
that,
differentiate, just cancel.
Yeah. And this is in terms of x as well, and here we're anti-differentiating in terms of u, so it's a different variable as well.
So will those variables always cancel?
So for this type, then yes, that's
Yeah.
going to count.
If like you're using u and x, one of those variables will cancel each other out.
Yeah,
Okay.
yeah,
Right.
yeah. So the x variable, when we get to our final bit, which is here, so it's now u squared du that we're anti-differentiating. So now what we're working with is in terms of u, not in terms of x. And you can see here this one in terms of u is much simpler than the one in terms of x. So to anti-differentiate a polynomial, increase the power by 1, divide by the new power, plus some constant. Now, of course, that was the substitution that we're after. We've now got to substitute back. And I'm going to squeeze this one down in here. And so that's cos cubed now, isn't it? Cos cubed x over 3 plus c. Because our original question was in terms of x, so we need our final answer in terms of x. So we've made a substitution in the middle to simplify that integration process, and then come back. All right. So the next one we're looking at is this one here. So we've got b, and so we're looking at the integral of 5x squared bracket x cubed minus 1 to the half. Alright. Whoops, forgot my dx. Okay, so now finding, we're going to make a choice of what u is going to be. Remember, we're trying to simplify things. So out of all of this, the most complicated bit's this bit here, isn't it? X cubed minus 1 to the power of half. That's the most complicated bit. So a good place to start is to look at that most complicated bit and say, well, how can I simplify that? Well, I can simplify that if I let u equal x cubed minus 1. Because then it's going to be u to the half, which is more simple. If I differentiate that to u dx, what do I get? 3x squared? Yes?
Yeah.
So then, if I rearrange, dx would be du over 3x squared. So now, 5x squared x cubed minus 1 to the half dx becomes 5x squared, leave that there. The x cubed minus 1 to the half, well, that's u to the half now. And the dx, well, that's du over 3x squared. Now what do you notice? The x squareds cancel. 5's a constant, the 3's a constant, you can stick them out front. U to the half, du. Yep. So now, u to the half, that's easy to integrate, isn't it? It's just now a polynomial. So we increase the power by 1, from a half to 1.5, which is 3 over 2. Divide by our new power, which is 3 over 2, and then we've got plus some constant. Dividing by a fraction, what do? Flip and multiply. So that would be 10 over 9. And putting back for our u, x cubed minus 1 to the 3 over 2 plus some constant. Anything about that? Alright. So again, you see we're choosing something that simplifies, so that we something that's quite complicated, something that's more straightforward, and then substitute back in the end. All right, the next one. Part C that I had there, that was a bit of a mix of stuff. Now, if you choose the wrong thing to be your u, you'll find you get stuck and you end up with something more complicated. So then you go, oh well, change it and do another one. So here we go. I wonder if did I write this up properly? I'm not sure that I wrote it up correctly. What did I write? Did I write 3x? What did I write? E to the x or e to the x squared? Should be e to the x squared. Sorry. That's what I should have written. Yep, there's a square there. Sorry. Right, so we've got to anti-differentiate 3x e to the x squared. So again, you kind of say to ourselves in this case, all right, which is the most complicated bit?
E to the x squared.
E to the x squared is the most complicated bit. So what I'm going to do is make that bit less complicated. And so if I let u equal x squared, for example, that's then going to be less complicated. It's going to be e to the u, and that's easy to anti-differentiate. Du dx be 2x, excuse me, which then when we rearrange, dx is du on 2x. Make those substitutions. 3x is still there. E to the x becomes e to the u, and dx becomes du on 2x. And then, as has happened in the past, we've got some cancelling. So we then got 3 over 2, e to the u, du. Antiderivative of e to the u is e to the u. So we've got 3 over 2, e to the u plus some constant. Substitute back our x squared. So e to the x squared plus some constant. Anything so far before we move on to the next one? No? All right, now it starts to get a bit fun. So another technique that we can use, another thing we can use, is completing the square on something. So sometimes completing the square
It can be two different things. So it can be odd.
can be used
Let's state which one it has to be. Which one it is.
to put an expression
Which one's constant? Wait.
in the form of an inverse circular function.
I wouldn't worry about that.
Derivative of.
It makes sense both ways.
So, let's have a look at what I mean by that. There's two examples. Do example A first of all. Alright, so this is one on that polynomial. So, quite complicated. To rewrite that, I'll rub this off in a minute so I don't. Down up at the moment, to the -1 doesn't really help us all that much. But remember, I haven't got it up. Remember when you look at your formula sheet. So get it up quickly. Special maths. Open that, thank you. Formula sheet. Their formula sheet. Come on. There we are. Down here. Where are we first? Here we go. There we are. So down here we've got something squared plus something squared. Alright, so if we could get it into this kind of form, then we could anti-differentiate. So what we're looking to do is we're looking to anti-differentiate x squared plus 2x plus 6. So if we could change this into this form, something squared plus something else squared, then we could use that. Now, if we complete the square on x squared plus 2x plus 6, I'm out of room there, so I'll do it over here. What do we end up with? Alright, so we've got x squared plus 2x plus 6. I'll make a perfect square out of that stuff. So down here I'm going to have x plus 1, is it?
Yep.
So come back, plus 1 here, then I need to minus 1 that I've added, so plus 5. So something squared plus something squared, is that what? Root 5, yeah. So what we've got is x plus 1 squared plus root 5 squared. Alright, so that now looks a bit like that. So what have we got? Let me rewrite that then. So we've got 1 over x squared plus 2x plus 6 dx. And we're now saying that looks like 1 over root 5 squared plus x plus 1 squared. Alright, so that looks like the inverse tan one now, doesn't it? Yes?
Somewhat, yes.
Somewhat. Except the inverse tan one that says a squared, well that's alright. We've got root 5 there, that's alright, that's easy enough. We should need an a up there, but we can get that easily enough, can't we? I'll just by going... Just by doing that. So that bit's easy. But the other tan one just says x squared. But we've got x plus 1 squared. So now, when we do our substitution, this is the bit that we want to...
X plus 1 equals u.
X plus 1 equals u. That's exactly what we want to do, isn't it? Because if we can do that, then we'll have u squared there. Then it looks exactly like our tan one, yeah? So let u equal x plus 1. Du dx is
1.
1. So what that means is that dx is equal to du. Yes. So then what have we got? Well, we've got 1 on root 5. Root 5 on top here. We've got the root 5 squared there. Plus u squared. And dx is du. And so now we can use our inverse tan pattern, yeah? So our inverse tan pattern says that that then is, leave that 1 on root 5 out there, it's tan minus 1 of u on a, and a is root 5 I believe, plus some constant. And so now we just need to replace that u by, well, it's got x in it, so that's x plus 1, isn't it? And there's our final answer. Nice and tricky. Oh, you don't have to, do you like that? Hey?
No, I like it.
Hey?
I said, don't jinx us.
dodge answer.
No, he said that wasn't too bad, and I was like, don't jinx it.
Don't jinx it. No, it's not too bad, is it?
No.
There's a lot of bits going on, but each of the individual bits are not too bad. All right, so the other one on this one is this. We want to find the antiderivative of, this one's got a 3 on the top, and the bottom it's got root 9 minus 4x minus x squared. Dx is what we're after. So now again here, with this one, you've got a root on the bottom of some stuff. So again, there's a root on the bottom of some stuff. Something squared minus something squared. And so you kind of need to try and, if we could change this in here into something squared minus something squared, we'd be in the same situation as we were here, and it would be either a cos or a sine. So, complete the square on. Minus 4x minus x squared. Alright, so first thing I'm going to do is I'm going to take negative 1 out as a factor. Because we're used to dealing with positive in front of that. So the x squared plus 4x bit becomes x plus 2. We need a plus 4 in there, we're going to take 4 away there, so we're taking 13 there, aren't we? Now when I put that minus 1 back in, what do I end up with? Minus x plus 2 squared minus times minus 13. Something squared minus something squared.
Yep.
Root 13 squared minus x plus 2 squared. Yep. So it's looking like a sine or a cos. Alright, so 3 over root 9 minus 4x minus x squared. So what do we got? We've got 3 over square root of root 13 squared minus x plus 2 squared. Alright. Positive up the top here, isn't it? Positive 3. So positive 3. It's looking like inverse sine then, isn't it? Alright, but with the inverse sine it's 1 over. But we can deal with that easily enough by doing what? 3 at the front, yeah. Alright, for our substitution, what are we going to do? What are we going to let
U
u
is
equal
equal to x plus 2.
x plus 2, yeah. So u is x plus 2, du dx is 1, which means that dx is equal to du again. Alright, so when we go there, now we've got 3 bracket 1 over square root of root 13 squared minus u squared du. 3 lots of sine minus 1. u on root 13 plus some constant. Make back our substitution. X plus 2.
Will you get a mark taken off if you could get the plus constant?
Yeah, if it asks, the question asks you for the antiderivative.
If it was an,
If it an, you don't have to put it there, because an antiderivative is plus 0, or plus 5, or plus 20, or plus whatever. It is an antiderivative. But in this case, the antiderivative, because you haven't got information to work out what the constant is, you need to put plus C. Otherwise, yes, you will lose a mark. All right. Now, sometimes, we're going a lot here, actually. So tomorrow might just be a work session. Might be. All right. Sometimes we need to substitute for x when we, and that substitution is going to include something with u in it. So some examples I'm going to look at. I'll look at 2 examples. In this case, Tony, here's this question here is find an antiderivative.
Yeah.
Right, so this time I won't be putting the plus C. Alright, so the first one is 2x plus 1 times the square root of x plus 4. Sorry?
Is it find an antiderivative?
Oh yeah, I forgot that, didn't I? And antiderivative. Find an antiderivative of the following. Alright. 2x plus 1 root x plus 4 dx. Alright. Now. Any ideas what we might choose to be our u, let u equal? The one that's more complicated is generally...
Yeah. Is that, I'm just trying to, is it
So which one's more complicated?
square root of 4?
Square root of, yeah. So let u equal x plus 4. So when I say look at the one that's most complicated, it may not always work, but it's a good starting point.
Is it just x plus 4?
Just x plus 4 for the u. Yep. And du dx is 1. Now, in some previous things that we had, remember we had some cancellings out,
Yep.
but now because we still had some x's in here, well now we haven't got that, but we've got an x in here. So the way we deal with that is we can say, okay, in terms of u, x then would be equal to u take 4. So when we do the substitution, I'm going to substitute here for u, but I'm also going to substitute that as well. Of course, this one here, we just dx is equal to du. So, I'm going to have 2 lots of u minus 4 plus 1, and then u to the half, and dx is du. We all right with that? Yes, so far?
Yeah.
Good? Alright, let's expand this stuff here. So we've got 2u minus 8 plus 1 u to the half du. 2u minus 7 times u to the half du. Expand that bracket out. Expand that bracket out. U times u to the half. What do we do with our powers? Add them. So that's 3 over 2. Yep, 1.5. Minus 7 u to the half. Du. What have we now got here? A starts with P. Polynomial. So we've changed something here that had a root in it. And because we've got x plus 4, that's what made it more complicated. So by making that substitution and simplifying that down to just u to the half, we've now multiplied in. We've now got a polynomial, and when we anti-differentiate polynomials, increase the power by 1, 5 over 2, divide by the new power, increase the power by 1, 3 over 2, divide by the new power. Because it's an antiderivative, I don't need the plus. What do we got? So that's 4/5 u to the 5 over 2 minus 14/3 u to the 3 over 2. Hope. Got that right?
Yeah.
Put our x plus 4 back in. And there we go. Next one.
How many more are there?
This is the last one. Alright, so in this one, for part B, we are looking at the antiderivative of 2x plus 1 over 1 minus 2x, 1 minus 2x squared. Alright, we'll let u equal what?
Let u equal 1 minus 2x.
1 minus 2x is a good choice. Just remember, we've got to simplify things. Alright, so du dx then is -2, which means dx would be du over -2. The other thing we're going to have to do is we're going to have to do something with this up here. So
Make x the...
make x the, yep,
that u plus 1 and 2. No.
Yeah, would that be right? I hope that's right. Now, in this case, I'm not going to go any further. Why am I not going to go any further?
It's already correct.
Yeah, it's got 2x here, so I might as well just leave that. Oh, no, it's going to, you could change the text, but this just saves you a little bit of work in the end. All right, so let's have a look. So 2x is 1 minus u plus 1 over u squared.
No, you meant to.
Dx is du over negative 2.
You can do that part.
All right, what can we do? It's negative 2, what am I going to do with that? Stick it at the front, yep. Negative half. 1 plus 1 is 2, so we've got 2 minus u. Now, I'm going to rewrite that.
Just multiply by 5.
So how can I
Don't you
rewrite this?
U times u.
Yeah. How else? I can bring that up to there, is what I'm getting at. Bad first question.
Yes.
If I bring that up there, that's u to the negative 2, yes?
Oh, true.
And then when I multiply that into those brackets, 2u to the negative 2 minus u times u to the negative 2 is u to the
And you wrote it very wrong.
negative 1.
I use.
Is that correct? All right. Then, so then we've got negative half. 2u to the minus 2. Now, the u minus 1, you might not recognise it, but that's 1 over u. And when we anti-differentiate, I should say, 1 on u, it's related to
Log of.
log, yes. Yes. So negative half, this one's simply just a polynomial. So increase the power by 1, divide by the new power, minus log to the base e, magnitude of u. Because it's an antiderivative, yep, we don't need the plus c. All right, now, let's neaten this up a little bit. Bring that down the bottom. Negative 2 there, I'll put that there. This is whatever it is. Put the u back.
Where did the dx?
Sorry?
Where did the dx?
That shouldn't be there. Yeah, sorry, where did the dx go? When we did our anti-differentiation.
Ah.
Oh, that should be,
I've
written the wrong thing, haven't I?
That should be the.
du, yes, du. So it's not dx at all, sorry, I've written the wrong one, haven't I? Sorry, my bad. Yeah, because I changed the dx into this and then I shouldn't have done anything with that, of course, should I? All right, so then, yes, it gets used when we do the anti-differentiation. All right, let's substitute back. What was it? 1 minus 2x. And then, if you wanted to, you could then multiply that in there. If you multiply that in there, that becomes 1 on 1 minus 2x. Negative times the negative is positive again. And what's that, a half? Log to the base e of 1 minus 2x. And there's our answer. All right, I did get through it all. So tomorrow we'll work on questions tomorrow in class.